So we here at Wisconsin have a particular brand of robotics in HCI, and you can characterize this as human-centered computing and robotics. The kind of robotics that we do is always human-centered with the technologies that people use. There's always some human involved in the picture. The HCI group, similarly, I talked about how we talk about computer systems for human use, we want to design them, and that's what the field is all about. So we have a number of faculty, mainly in computer science. There are other people in other departments. The list I have here is our computer science faculty, plus a few more people who work closely with us that are affiliates. So there's myself with less facial hair. I work at HCI and robotics, both areas, the intersection of that. Mike Fletcher works in HCI and robotics as well. He also does some information visualization. He's currently in Washington, D.C. He's not here today. Rahul Chatterjee, I think, is going to talk later about security. He works in the intersection of HCI, security, and privacy. Martina Rao is a computer scientist by training. She's in the education psychology department. She's in education technologies. She's a member of our HCI group. Then we have a number of roboticists on campus. Josiah Hanna is a new faculty member. He's joining in the fall. Fresh to start working with you guys. It's going to be very exciting to see you in the fall. He works in robotics and AI, particularly reinforcement learning. Mohit Gupta is part of our computer vision and robotics groups. And he builds really cool cameras that can capture things that other cameras can't capture. There are two more faculty members in robotics that are not in the department. Mike Zinn works in robotics. He's in the mechanical engineering department, but we work very closely with him. And he has the coolest picture there. I think that was some documentary director shot him. And then the last one is Rob Radwin, who intersects between HCI, ergonomics, and robotics. He's in the industrial engineering and biomedical engineering departments. Okay, so we have a core group on campus that is spread across different departments, a lot of people in CS, and there's a broader group that you can learn more about using two websites. One is our HCI group website. This is the campus HCI group. It lists all the people, the courses that you can take and whatnot. It's very simple. It's hci.wis.edu. Okay? We also have a campus robotics group website, robotics.wis.edu. That will also give you pointers to people, classes, and things like that. Okay? All right, so that's my intro of the areas broadly. We have faculty, we have classes, we have all the good stuff. What I'm going to talk about next is to really get into what human-centered computing and robotics might be all about. Okay? We are interested in new technologies that we are not used to seeing yet. Okay? We're thinking about 20 years out, technologies that people use to make deliveries, technologies that people use for personal reasons to motivate themselves, technologies people use as collaborators, even conventional technologies that may not look robotic, but they have robotic features. So we're interested in two things with respect to these technologies. Okay? First, how do we build them? Right? They have to be systems functioning in the real world. How do we build these work? And we are being one of the strongest systems departments in the country. We really focus on that. The second part is once we have these systems, once we build them, we need to understand what happens to people who interact with them. Are they actually working well? Right? When we're designing them, are we understanding what it is that they need? How should the technology be shaped? So there are these kind of two perspectives, and that actually represents the research philosophy. I talked about being human-centered, and what I want to show you kind of a glimpse of is how do we go about that? How do we actually do human-centered work? And then the way to think about that is really a process of looking at people, building systems, looking back at people. Okay, imagine this cycle where you start first understanding how it is that people interact with each other, what is it that they expect from each other, what are the things that people worry about in their day-to-day lives, and kind of extract information from them using computational tools, build models, and we can put these models into platforms. These could be computer systems, robots, whatever, and at the end evaluate those systems with people again. Okay, let me give you a quick example. So we were interested in building a robot that could look at its user, particularly look at the gaze behaviors of its user, and provide proactive help. And what we wanted to do was to first follow this process, to first look at how people do this themselves, right? If you go to Subway sandwiches and wanted to order a sandwich, how would you actually go about doing that, right? You look around, you look for foods, you refer to foods, talk to people about them, and they serve them and like that. So when we do this kind of, we call this a modeling study, we actually have to capture lots of data. We think about, okay, how do we actually look at different combinations of people, right? And large groups of people, tall people and short people. So we want to kind of capture that variability, we quickly want to turn that into computational signals that we can actually model, okay? And the data usually looks very messy. It can look like something like this, right? What you're seeing is someone requesting a sandwich, a fake toy sandwich, okay? And then a worker was putting together the sandwich, and what you see, the orange dot is the gaze focal point of the two people. It's very complex data. Things are moving around constantly. They're looking at things they're talking about. They're talking about things that they're not looking at. How do we actually, model this mess? Just a quick example of what we can do. The graph you see here on your left is over time, we start estimating purely based on their gaze patterns what they might be interested in. Okay? Over time, we see them going back and forth to different items. At some point, we get confident enough that, I'm going to call the shops now, and it's going to be this, right? It's going to be a pickle. At that point, we make a confident prediction, and at some point, the pink data is where a person verbalizes what it is that they're interested in. They say pickle. Okay? When we're confident enough to make a prediction, when we actually verbalize it, this window we call an anticipation window. In our original data set, that window is about 2 seconds. Okay? So 2 seconds before someone says something, we can actually predict what they're going to request, with this lead in advance, right? And we can do that at a pretty good level of prediction. With a baseline of 4%, we can go all the way up to close to 8%. Okay? So now what happens? Okay, I have this model that can look at the gaze patterns of someone and predict what they're going to ask for. Now we can actually put that on a robot. Okay, this is a robot that we designed to serve smoothies. Again, we do fake smoothies because we don't want to do cleanup after experiments. But those little foam blocks are smoothie ingredients. They're blueberries and pineapple or whatever. And people are asked to request, from the menu what it is they want. So here you go. The person is given instructions, and then he's looking at ingredients. As he's looking, the robot is predicting what it is that they're going to ask for. And now my audio is not working, so it's not a big deal, but he said, "Can I have blueberry, please?" Once the robot heard the confirmation, it wished for blueberry, and I put it in the blender. And turns out that if your prediction is correct, we can go all the way up to 3.2 seconds of lead time. What this does is that it makes robots very smooth and fluent. Before you ask for something, the robot's already going to get that, right? It's similar to how Amazon now, you're shopping and you're trying to figure out which book you want. They already predicted which book you're going to buy, and they already put it in the box, right? It's on your way. This is one example of how we start where people build models, put it in systems, and put it in front of them so that people can experience these systems, okay? So in general, when we're thinking about systems, we're talking about two types of systems. There are two types of, we call these agents. They're either physical agents that help you do physical work. Okay? These are usually robot arms. You put them on your kitchen counter, it will help you unload the dishes and clean up and declutter and whatever, right? And social agents. Maybe this is a character, like a voice assistant, but it has a body, and then it helps you maintain a medicine regimen, whatever it is, right? So we work on two types of systems. What I want to do is actually give you a few examples of ongoing projects. Most of these are collaborative. I'm talking about them. I'm talking about the ones that I know the best, but it's kind of distributed across different faculty members and groups. So I want to talk about 4 projects. Okay, the first project is in the physical domain. Okay, about 12 years ago, the robotics world said that, hey, enough with these robots that we put in factories and we have to cage them. They're so unsafe. Sure, they're efficient, but it's not flexible to use. So they decided to reduce the power that these robots have and give it a little bit more environmental awareness so that they could be safe and put it in the same space as people. Okay? These are called collaborative robots. The idea is that they're easy to program and they're inherently safe. So you can take them and put it, you're on the shop floor, you move it to your bench top and have it do some things for you, right, very easily. The challenge is that these are actually not that easy to program. What we wanted to do was to make them so easy that it would be almost as if you're moving your own hand. Right? You move your own hand and that controls the robot. What that does is either real-time control or you provide input into the robot with some kind of programming or training. Okay? Turns out that there are a lot of technical challenges here. The geometry of my arm, the geometry of the robot are very different. Transferring motion between those geometries actually has its challenges. But we did some really interesting technical work here to solve that problem. And at the end, we can do very, very complex tasks in real time. This is a user who has no training in or experience in interacting or controlling a robot. And all we're measuring is the position of their wrist at 6 degrees of freedom. Okay? As real-time input into the robot. And they can do very complex tasks like playing with Tinker Toys, folding shirts, decluttering a countertop, and stuff like that. Right? If you wanted to actually program that task using the programming tools that these systems come with, it would take you an entire morning. Right? Here we can do this in real time. And like I said, we can do more complex tasks. Well, this is very nice. We were satisfied with this in general because it is better than the state of the art. But it requires that you're next to the robot. What if the robot is somewhere else? Imagine you're Houston and there's a robot on the space station, and you want to control that to do different repairs. So here we decided, okay, well we can solve this problem too. We put a second robot next to the other robot. We gave that robot a camera and said, hey, your job is autonomously to give the operator the best view that you can get of the task space. Okay? Now, what the robot knows is the robot that the operator is controlling and its geometry. It doesn't know anything else. It knows a little bit of environmental awareness, like what the geometry is around here, so that it doesn't run into things and it gives you the better view. Here's a video of that. On the left is the operator's view. They're getting this video feed from the robot that moves the camera. And a camera robot is looking at the arm robot that's doing the task, and based on its position and geometry, it's trying to give an unoccluded view of the task space. It's also intelligent. It would, for example, if you're moving very small amounts, it knows it's a focused task, it would zoom in. If you're making gross motions, it would zoom out. If you open the drawer, it would actually kind of look inside from the top because it knows that you need that kind of a view rather than just a naive view. And this again blows everything out of the water in terms of the state of the art, which is kind of putting an array of cameras, putting a camera and effector with a manipulation camera, methods that don't work really well. Okay, so we were happy with that too, but we weren't entirely happy. What we wanted to do was to do really complex tasks. Okay, imagine something like this. So this lady was asked to make a fake recipe. I'm very good at fake recipes in this department. They are mixing a lot of things, they're putting away containers, they're stirring things, a lot of manipulations using two hands and complex manipulations, right? Can we actually do things like that with a robot? Does take a little bit of work, but we were able to do that too. So here's a bimanual robot that's controlled by a naive operator who's never controlled the robot before, okay? They are just moving their arms, controlling the robot. We're mapping the two arm motions to the arms of the robot, but you have to do some coordination there, okay? If you don't coordinate those arms, what happens is that someone's holding that colander and then they drop it or they crush it, right? So we, for example, detect that they are have a fixed offset manipulation, and we blend in a shared control signal to effectively do that. And we can do very, very complex tasks, and they're doing a fake omelet here that we're very satisfied with. Now it's time to actually use this technology in cool stuff. Okay, we have a partnership with the Boeing company. They're the ones who made the planes that you flew here with, funded by NASA. People who build these airplanes. Imagine day in and out, they are doing thousands and thousands of operations every day on the body of that airplane. We're interested in putting these robots between those people and the manufacturing tasks, such that all they're doing is actually controlling the robot to do the task, so that the tasks can be more effective and safer for them. Here are some of our first few prototypes where you're getting some kind of real-time feedback from an interface, and providing real-time input into a robot and performing some toy tasks. This is sort of just 3 months into the project. We're hoping that this will actually become as compelling as some of these demos that you saw. Okay, all right, so that's one big project example I wanted to give. The next example I want to give is the social agents domain. Okay, this is an interesting domain too. We saw how voice assistants picked up, and how many people here have a voice assistant in their home? It's a Dot or an Alexa, whatever, right? About half the people. And it happened very quickly, right? And our expectation is that this will happen with robots too. They will quickly enter your spaces, you'll start using them. What's going to happen then? So I've worked in this space for about 15 years, and now our knowledge and technology is actually mature enough that we can build integrated systems that we can deploy. This is an example project from that intention. The idea is that we built a robot that helps kids read, okay? So that's my grad student pretending to be a kid. And the idea is that kids would read to the robot, right, as if they read to their parents. And the robot knows the story and will actually comment on the story. And it knows what books you've read. It will connect the different books. It will connect the characters, find similarities, and have a conversation with you. It'll help you choose books based on your interests, and it'll also help you set reading goals and things like that. We did things like, okay, this was our envisioned use, right? We wanted this nice, clean countertop, and books that are laid out really nicely, and they're sitting down reading with the robot. In reality, kids want to read in beds and whatever, and you can see that black tape on the robot because it kept falling and stuff like that, right? So these field deployments give us a lot of information about how do actually people use these systems. Then we start comparing them to other things and actually deploy them for a long period of time. This is data from a 14-day deployment we did 2 summers ago. And we can see, okay, compared to their reading goal, how much are they reading? Are they more motivated to read? Do they understand the topic better? And stuff like that. We get this really valuable data from the field. And now, we don't hate ourselves enough. We decided to do an entire summer deployment, which is really hard. So this coming summer, in partnership with a community center in town, we're going to do some science reading, okay, for the entire summer. We're prepping the robots, and you should see the HCI lab right now with armies of robots program to be put out there. Okay? The third project that I'm going to talk about comes from the intersection between all these things that I'm talking about and research and programming languages. Okay? What we want to do is we're going to build design and programming tools for people who are eventually going to design these applications. Okay? Right now, the prevailing wisdom is that there will be robot manufacturers, okay, producing these mass manufactured robots, and then they will somehow end up in people's homes. Somehow end up there and be able to do all of the things that they're designed to do. In reality, what's going to happen is that there's going to be some kind of step in between where you have a designer who will take this general purpose robot and actually create a customized application that will be deployed to various domains. If it's an education domain, then the designer is going to create an education application. So what we started doing is building programming tools that will give people very powerful programming environments and mechanisms. But that's not the only thing that we want to do. We want to actually use the power of programming language and methods to analyze those programs as designers create them and tell them, give them feedback about the quality of their design. So what we do is we give people a visual programming environment as they are dragging and dropping things, and they can actually create very complex programs. We turn those programs into entire transition systems that we can analyze. Then we can do things like define correctness properties. We can say the robot should never do this. The robot should always do this. Every time the robot interacts with the person, it should greet the person. And if the person's design didn't include that, it's not going to satisfy that correctness property. Right? We alert the designer, and sometimes we just go fix the program for them. Right? This is a very powerful tool, and one of the best people over a couple years ago, we're very happy with that. A second tool I'll talk about in this domain is, well, maybe we don't need to even give the designers this visual programming environment. Maybe all they need to do is to demonstrate to a system how the robot and the person will act. So what we did here is that we augmented people with microphones and armbands that capture their gestures and speech and create sort of mid-level abstractions that represent interaction and create programs out of that automatically. Okay? So I have a video, but I don't have audio. I'll have to talk over it. So this is a tool that we call Synth. The idea is that we want to create these interactive programs. We can ask designers to wear microphones and armbands that will capture their speech and their motions, and then turn that into what we call interaction traces. And you can take these traces and learn a program that satisfies each trace. Right? So at the end, you end up with a program that can accommodate all the examples that the system saw. Now, the power of this is that you could immediately implement that on the robot and automatically see it in action, right? Designers are acting out, and then they're going to the robot and testing it. Acting out, testing it, right? And they can also do editing and stuff like that. Our current project, which you can see in the HCI lab this afternoon, is we have a tabletop interface with little figurines, and we move those around, and you create a program based on that, and the robot immediately demonstrates it. Okay, the last project I'll mention very briefly is a collaboration with a psychologist colleague of mine, and we have been very frustrated with how emotionally unsophisticated agents are, from voice assistants to robots to autonomous vehicles or whatever, right? So you talk to your Siri, and it gives you this very blunt, very literal response, despite all the clever things they've programmed in them. Our goal is to make them more emotionally sophisticated, and the idea is that, again, we can use this approach that I've been talking about, analyze and model human interactions, and utilize physiological signals to create what's called a functional model of emotion. The idea is that I can model contextual factors as well as people's behaviors, and then put that model on a system when that context arises, and when it encounters those behaviors, we'll know what to do. Okay, it's a very exciting project, and I'll be very happy to talk about that more. To learn more about this stuff, I'll be available this afternoon to talk to people. You can visit the HCI lab to see some of these demos. It's on the 3rd floor. My students are going to be expecting people between 1 and 3 o'clock. And also visit these websites to get more names and courses and things like that. Okay? Enjoy your time in Madison. I look forward to talking to you this afternoon. Thank you.